Okay, let's talk about boolean functions. So we've established a boolean algebra, and we're working with one or more variables, named variables, call them X, Y, Z, W, Q, whatever you like. Each of the variables can have one of two values, 0 or 1. And we have binary operators and an or that we can manipulate, we can act on these variables with. So we've got enough of an algebra that I could write a thing like this. So we're going to need to know a couple things. Just like ordinary algebra, we're going to need to know about the order of operations in order to parse what the heck this means. And the order of operations that we're going to use P-now, P-N-A-O, parentheses, negation, complement, parentheses, not, and, or, in that order. Okay, so the first thing we do is check to see if there are any and operations. And remember, the and is represented with a dot, and sometimes in ordinary algebra, when we mean multiply, we just squish the two numbers next to each other and call that multiplication. So this expression is the three-way and of the complement of x, the complement of y, and z. This expression is the three-way and of the complement of x, the complement of y, the complement of x, uncomplemented y, and uncomplemented z, and so on. Okay, so the job, like what function is this? What is it doing for us? And it's a good question. But in order to figure that out, we need to ascertain what are the conditions such that the function f is logical 1 asserted, and what are the conditions such that it's logical 0. In order to do that, we have to sort of chase through the different logical expressions that make up function f. Now, okay, so let me show you what I mean. We have input variables x, y, and z, because those are the named variables in our deal here. Sometimes x shows up complemented, sometimes it doesn't. That's fine. X, y, z. Those are our three inputs. Now, those three variables could each have 0 or 1 as their value, and we're interested in any possible combinations. So, okay, so there are three variables. Each of them could have two values. So we've got two choices for the first one, times two choices for the second one, times two choices for the third one. There are 8 possible things that could happen. The easiest way to make sure we get all 8 is to count up from 0 in binary. And once we get to 1 less than the number of things that could happen, because we started with 0. 0, 1, 2, 3, 4, 5, 6, 7. Wait a minute, what did I do here? 0, 1, 2, 3, 4, 5, 6, 7. But I'm showing 8 fingers because I started with the 0th one. So that's 1, 2, 3, 4, 5, 6, 7, 8 possible things. And if you, that's the whole story. There's no other possible way to combine values for the 3 variables x, y, and z that isn't represented here. Each row represents a possible input state, and there are no other possible input states. This is the whole list. So if we're going to construct this this like logical table, a table of logical values, call it a I think the textbook calls it a truth table. Table of when f is and isn't true, logical yes, high value 1. A truth table. How many rows are there in our truth table? If we're dealing with the number, if n variables, in this case 3, there are going to be 2 to the n rows in our table. We've got 3 variables, there are 8 rows in our table. Okay. Along the way, we're going to need x complement and y complement. We're going to need complemented forms of x and y. So, okay, so and that's not so bad. We can just, whatever value we have in the x column, we can find its complement. In other words, the value that isn't that. So we've got 1, 1, 1, 1, 0, 0, 0, 0. The y column 1, 1, 0, 0, 1, 1, 0, 0. We just put the opposite of whatever we had for the value of that signal, and that's the complement of that signal. Okay, cool. So now we can start to build these logical expressions. And notice that I'm following order of operations as I go through this. Parentheses, there aren't any. Negation, that's this blue stuff, and then or. So I'm actually going to ask for the and of x prime, y prime, z. And there I go using the word prime because, yeah, algebra. It's familiar to us. When I say prime, what I mean is the complement of. So this logical expression asks the question, is it true that all of these values, that this and this and this are all true? X, not y, z. So we're looking at these three columns in our truth table, and we need all 3 of them to be 1. It doesn't happen here. It does happen here. It doesn't. It doesn't. It doesn't. It doesn't. It doesn't. There's only one time when not x, not y, z, not x and not y and z is all logically true. And then, okay, so the and statement is logically true then. We can do the same thing for not x, y, z, and x, not y. And just quickly, so that's this column and this column and this column. So that's these three columns and it together. So, okay, so we need all of them to be 1. No, 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 yep, no, no, no. X, not Y. So that's, all right, we gotta look a little farther. It says this column, the first column, and this second blue column. And we need both of them to be 1. No, 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 yes, yes, no, no. Okay, and the last step, function f is the three-way OR. Is it true that either this or this or this is true? Well, there's only 4 times. 0, 1, 0, 1, 1, 1, 0, 0. Okay. So we've made ourselves a truth table for function f. We know now what function f does for us. It is a way to sort of select or accomplish a job when that job requires a value of 1, when x, y, z, it has this particular input state, or this particular input state, or this one, and only for those input states, and a 0 for the others. But that there's some task we need to perform or could need to perform such that that would need to be true. I'm not sure why, but it's, what it does is, for now, not the issue. The question is now, all right, how do we write it? And once we've written it, what is its behavior? And so there we go. Now, we said a second ago that these operations and an OR can be expressed using logic gates in an electrical logic, an electronic diagram of gates and combinations of things. Okay. What would that look like? Along the way, you have bumped into other logic gate signals. So we've got X, Y, and Z. We're going to need X complement for a couple things. So let's keep input X because we're going to need it for this last term, but let's also ask for, let's tap into that line and ask for let's use an inverter, a triangle with a circle on the end. That's our symbol for negation. So here we've got X prime. Let's do the same thing for input Y. Use an inverter to get not Y. Input Z, we just need. We don't need its complement. So the and of not X, not Y, and Z. All right, so I'm going to put that, let's see, I'm going to put that here. and of not x not y z. So we tap the not x line, we tap the not y line, and we tap the z line. That's our first term here in what looks like an algebraic expression. Well, a boolean algebra. It's the first boolean term. Not x. All right, so I gotta tap that before we get to that. Not x. Y. This line comes from the unnegated, uncomplemented input y. Z. And we can AND those together. And the last one is an AND with x and not y. The outputs of those three AND gates, now those three AND gates are the three terms in our functional expression. But we still have to OR them together. So we need a 3 input OR, and that's function f. So we need 1, 2, 3, 4, 5, 6 gates to use logic gates, digital logic gates, to represent, to achieve the functional requirements of this function f. Or do we? We could use the postulates and theorems of Boolean algebra to make some simplifications. These first two terms have x prime z common. And we're allowed to do this because these functions are distributive. This is the AND of not x and z, ANDed together with the OR of y and not y. And because things are associative and things are distributive, we can factor just like we factor in normal algebra. But thing or not thing, all right, so if it doesn't matter, that's one of the identities. This thing in parentheses always has the value 1. Either this marker is black or it is not. We got that. That's a true thing I just said. This evaluates to logic 1 all the time. And 1 and some stuff evaluates to just some stuff all the time. This term is still here. So this starts to look now like x prime z or x and not y. Nicer expression. Same function. Same truth table. But different circuit. X, y, z. We still need an inverter for x. But I mean, I guess technically we still need an inverter for y, but we could just start with the complement of y, because that's all we need. I don't need the uncomplemented y, not like I do for this term in the original expression. So it's already y complement. Z and we need regular x. Okay. Not x, z. Regular x, not y. Or those together. We're done. 4 gates instead of, what did I say, 8 or 6 or however many. This is a savings, right? It's easier to implement this than it was to implement the other logic diagram that I made a minute ago, even though they have the same logical job, function f. So my takeaway from that is that we need to know how to simplify Boolean functions. Like, I feel like this is a thing we're going to be doing all the time, right? Because I always want to get the simplest possible, the least complicated, the most cost effective, right? If I need 4 gates only instead of 6, I can use less material, right? It's cheaper to manufacture. I can put it into a smaller space on an integrated circuit if I want to do that, onto a circuit board or something. So this kind of simplification, we're going to want to be able to make it as quickly as possible, right? Because it's going to be the thing that stands in the way of our design being implemented in the most efficient way. That this simplification happens in the middle. So we're going to want to get really good at it and not have to kind of guess whether we're making the right simplification. Is this the simplest way? I don't know. I can try to mess around with the algebra and find a simpler way, but I want to be sure. That's what chapter 3 is about, is developing an algorithm that we can use over and over and over again to simplify Boolean functions and simplify the associated logic diagrams to implement those functions. In order for chapter 3 to really work, though, there's a little bit left for us to do in chapter 2. We have to build up the formalism a little bit for writing, for expressing Boolean functions. Once we have a formalistic way to express Boolean functions, we'll have them in a form that we can apply algorithms to easily simplify. That's the goal of the next bit. I think it's the last video segment for chapter 2, and it's the next one.